Yes.
Okay, so Mike asked me to talk about, well, this is something I brought up for the time domain subgroup, and so it didn't get much viewing within the AGN sort of part of the collaboration, so it'll get a broader view here. So the idea was mostly to track the sort of extreme variability and the changing look or changing state AGN, which we would see, sort of in the time domain. And so for definitions here, variability, variable accretion AGN would be sort of a changing state, as it were, of accretion. And then the variable line of sight column, or AV in the optical, would be changing look. Those are at least my definitions. In the literature, these are often blurred, or just everything is assumed to be look. So broadly speaking, to zoom out, we have a ton of questions about AGN, how can we understand the AGN physics of accretion and ionization and all that? How is that related to the overall structure and maybe the evolution of that structure? And then we want to understand how that is all interrelated to each other. We want to understand how the black holes grew, how they became linked to their host galaxies, why some supermassive black holes are AGN and some aren't, right? How that links again to their host environments and larger scale environments, how the AGN might impact their host or their environment. And then, finally, a sort of interesting question is how can we harness AGN as cosmological candles, which at the moment, we've shown some efforts in that direction just to say they could be, but we really don't have any samples where they're competing yet with other cosmological tracers. And I think in the next 20 years, probably we will. So to put everyone on the same sort of scale here, I'm just showing, your Astro 101 version, or maybe Black Hole 101 version of what we sort of know about AGN. And so we have an accretion disk, we have the black hole. The accretion disk is a multi-temperature disk, and the optical and UV. It then, there's a halo of a corona of hot electrons. So if we see here, and these hot electrons will upscatter the UV photons into X-rays, and some will go out, some will come back down and reflect off of the disk. And so I consider all of this sort of the central engine, and that relates to different emission mechanisms, which we see across the electromagnetic spectrum. So the disk is in here in cyan. Actually, sorry, the disk is in here in blue. The hot corona is in cyan, and maybe the soft excess of relativistic reflection is in magenta here. And then we have sort of larger scale reprocessing, which might be off of the outer disk, might be off of the broadline region, might be off of the torus here, which is not really in this donut shape, but is actually in clumps here, might be off of the narrow line region, et cetera. And that will give us emission lines that are sort of shown tiny here. That'll give us this hot dust component, and potentially that'll give us this reflection hump here in the X-ray, along with the fluorescence iron K alpha and other fluorescence lines. So that's the sort of broad structure that we know about AGN. And so within that scope, we can kind of interpret some of the unique phenomena that we've seen. And one of the first phenomena that was found when people started pointing hard X-ray telescopes at nearby AGN, and typically, one telescope would point and have an observation, and then another telescope would point a little bit later, with better signal noise or better properties, and find something completely different. And that was very puzzling. And so that was slowly realized in the early 2000s. And this is just an example of four the first sources that were seen. And they would change, they would change from, apparently unobscured sources to almost completely reprocessed sources. And what had to happen here was either that the X-ray corona had to completely disappear, but yet we're still seeing the reflection, or because the corona was so small, a cloud could, a broadline cloud or a torus cloud could move into the line of sight, obscure, and knock down the continuum flux, while we're still seeing the broader reflected or processed photons. And so these few objects were dubbed changing look AGN because the line of sight was changing on a time scale of a few years. And so in effect, we're kind of observing the weather of these clouds moving around the supermassive black hole and falling into our line of sight. And so we can think about this as a very unique probe of the AGN structure. But obviously it's a very particular probe because it depends on the line of sight that we're looking at. And so presumably these were seen in previous surveys, but not really distinguished from just variable accretion because the soft X-rays, you wouldn't necessarily be able to have enough information to tell the difference. So as we got more and more information, some objects were observed multiple times. And so one of the most famous ones is NGC 1365 with various telescopes by Guido Rizzoliti and collaborators. And in particular, they noticed lots of changes in the hard X-ray band. And you can see in particular the X-ray, the iron K alpha was popping up and down because this continuum was disappearing or appearing. And so what was happening was, we were seeing different clouds moving along the line of sight and obscuring the corona. And you could see the ingress of these with time. And let's say I don't actually have a light here, but I should have. And so because of this ingress, you could follow the obscuration with time and you could actually map out what this cloud looked like. And so this is an example of what we think one of the clouds looked like in terms of its column density structure. So it had this sort of cometary sort of view. And the idea is, then you can you're looking at one particular line of sight and you see these clouds move in and out. And so depending on what type of AGN you're looking at, you might see fewer clouds or more clouds and so forth. And this, of course, allows you to probe some of the potential structures of these clouds, whether they're spherical or toroidal or what have you. And so with more time, people found similar events in Compton-thin AGN showing column density changes from very minor column densities of 20.5 up to 10 to the 24 with partial or full covering, neutral and lowly ionized gas. And these are vary on timescales of days to 10 years. At the same time, even Compton-thick things like NGC 1068, which is our sort of Rosetta Stone of Compton-thick AGN, we actually with NuSTAR observed an unveiling by a few times 10 to the 24 over the course of many months. And so even in these very obscured systems, we can still see the X-rays leaking out and being blocked by line of sight clouds. And so at the same time, RxD had been monitoring several AGN and had actually seen some of these AGN go through, clouds pass along the line of sight. And so they were able to do statistics on sort of how often these clouds came and went. And so with that, not many sources had been monitored, but they were able to kind of probe the timescales of them, the column density changes and so forth, and actually place them. So I think the X-ray absorbing clouds are here in gray. And so you can see compared to the torus dust calculations, sublimation radius from the luminosity, they typically sat sort of inside in some cases or at the edge of the torus. And then these were the sort of broad line region for the different objects. And so in this sense, you can kind of understand the overall structure. Certainly when you use it in unison with the multi-wavelength data sets. A student of mine did a dig through the archive looking for variable iron K alpha emission, which is associated with this potential reflection component. This is the narrow component, so it should be more distant than the disk reflection. And we found in some cases very strong variability of the iron line, which was lockstep. This is the continuum variability. This is the iron line variability. And so you can see almost in lockstep the variability of the continuum is being reflected in the iron K alpha. Then there were others where you didn't see that, or you saw very little variation and was not necessarily correlated with the continuum variation. So in this way, you can kind of think about probing where the iron line is coming from and what what the overall structure of the material around the AGN is. And so from this, we actually found that these red points here are where we think based on the sort of light crossing time, where we think the iron line should be coming from. And we can also look at the dust sublimation radius in blue here. And so in general, all the red points are inside of the blue points. So they're actually the variability portion, or a portion of the iron K alpha, the bulk of the iron K alpha seems to be coming from broadline region clouds. And so this is a little bit of a different view from the initial picture I showed you, where maybe the bulk of the reflection is coming from the inner edge of the torus. And so we can kind of compare this to other ways of understanding the torus structure, which are typically from spectral modeling. And the spectral modeling tends to be very degenerate. And so, it depends on what angle we are looking at with the line of sight, what the potential structure is. If it's, if there's winds coming off in the dust, we're seeing the reflection from, dust in the ionization cones, whether we have a warped disk. So there's all sorts of possibilities that are degenerate in just the X-ray spectra alone. The variability can potentially help in understanding sort of where that reflection is coming from. And that could be used in unison potentially with the modeling of the torus or the dust emission reprocessing in the IR. Okay, so that's changing look AGN, as it were. On the variable accretion side, we've had a few historical cases which have had people scratching their heads for a while. And so Mercurian 1018, for instance, in the 1980s was seen to change from a type 1.9 based on the optical spectrum to a type 1. And then in 2016, it actually went back to a type 1.9, and it had 3 magnitudes of an optical drop in 8 years. And so this is the optical magnitude brightness of the so-called disk, and this is sort of where it sits now. And so H alpha varied by quite a lot between this sort of component. The Bauer decrement did not show any variation. And we don't have, so we have some X-ray emission, and so the X-ray emission looks like it also has dropped as well. And so we want to sort of understand what's going on. How can these, this is a much shorter time scale than the viscous time scale for the accretion disk to fundamentally change. And so we want to understand what's going on with the accretion disk and the corona to create these relatively rapid changes. And so, is this a disk instability? Is this a tidal disruption event inside of an accretion disk, or some sort of event that is opening up very briefly the disk and then it fills back in at some point? So these are all questions that sort of remain to be understood. Another couple of objects have gone through similar sort of transitions, and these were just sporadically kind of found from archival data. Sloan has been running spectroscopic survey over much of the sky, and has systematically done some multiple observations of quasars. These were all Seyfert galaxies that were relatively local, and so Sloan found a similar phenomena in quasars, where you see changes in the spectra, much more blue in one than another, lines disappearing, and so forth. And so these were also dubbed changing look AGN, although much more likely that something much more dramatic has happened to the accretion state of these objects. Although in some cases, there's an argument that it still potentially could be due to some sort of obscuration event. The typical timescales of variable extinction, for instance, should be of the order of many years for the crossing, the light crossing time. And this is sort of the same order of magnitude as the observations. These are typically taken in early Sloan data versus late Sloan data, so of order 15 years. But generally, the reddening is not very consistent with the observed properties. The variable accretion, as I mentioned, this should take 100 or so years, and this is 1 to 2 decks higher in time than the observations are telling us. Typically, about 0.1% of the quasars sort of show this effect. So it's a very small fraction, and so it's sort of not understood exactly what's going on. Very recently, we took a not so systematic search of the BAS. So the BAT AGN, it's a local AGN sample. We've tried to get spectra over the entire sample, and several of them, about 400, have multiple spectra. And in those multiple spectra, we actually found 14, and this includes several of the 3 objects I showed you before. The Seyfert galaxies showed some sort of change from narrowline to broadline, or broadline to narrowline on timescales of 10 to 25 years. And this is actually now, approaching something like several percent. And typically, these objects sit in this sort of black hole mass versus accretion rate plane, which is, they're not strongly accreting, they're kind of moderately accreting, not at super Eddington or anything like that. They're kind of at the edge where we might think below this, you don't really fill an accretion disk too well. And so it may be that due to, the sporadic sort of population of the disk, you may have these instabilities that come about. This is I say not really systematic, because we haven't really probed small time scales. This is the delta time between spectroscopic observations and the number of AGN that have multiple observations. And so this is kind of where we've been probing, but there's a lot of parameter space here still to understand. And so we want to sort of understand what's going on here. The X-ray observations in general are not as high cadence as the optical observations. For the few sources that have been observed multiple times, we think we see kind of 2 regimes, where this is the spectral slope versus the accretion rate in the X-ray related band. And you can see that there's sort of a high accretion state and then a lower accretion state. And maybe there's some claim to a phase transition here, which you can kind of see through various of these objects. And then broad lines have been seen in the optical for this phase and narrow lines for this phase. So there may be some relation between the changing state in the optical for the broad lines and what's going on in the corona, which is related to the accretion disk. And there's some similarities here between this, which is showing a comparison with AGN versus the different states of X-ray binaries. And so there's a suggestion that most of these objects that we're seeing are sitting here in this low hard state of AGN versus a more typical sort of high soft state, which we might be probing here. And so there's still a lot of work to be understood about how AGN fill this plane and the time scales in which they do that. One of the more recent interesting objects was 1ES 1927, which has been caught very early and didn't have any broadline and developed a broadline over time. And this is over sort of months time scale, and was also really heavily followed up by several of you as collaborators in the X-rays. And you can actually see that the corona here seems to completely drop out of this object, but then recovers and maybe settles back into what it was pre-state here. And the X-ray spectra are shown here. And so you can see very strong differences between the past state and the state sort of right in here, where the X-ray corona seems to have dropped out, and you just see a complete drop in the photons above 2 keV or 1 keV or so. And so what drove this event is sort of unclear, whether this was again a TDE in the accretion disk, an instability, and so there's a lot of work to be done in understanding all of this and finding more cases of this, and we can kind of think about this field in following the footsteps of X-ray binaries, like back in the 80s or 90s, when people were just starting to understand some of the different states of the X-ray binaries. And I think AXIS could really be a very interesting workhorse for this. So what will we know in 2030 when Access is supposed to launch? Well, we will have eRosita. eRosita now has 4 epochs. Maybe in the next 8 years, it will produce another 4 epochs or more, unclear. But obviously, this will be probing X-ray variability for something like 1 million AGN. And so we will have a lot of very sporadic statistics for a large number of AGN, which will be interesting and help us start to develop that. So I don't know what's going to come out of this. One can sort of predict it. Einstein probe is supposed to launch next year, and that'll sort of be a continuation of bat level light curves for maybe something like 1,000 or maybe up to 10,000 of the brightest AGN, but not in the hard X-ray. It'll be in a softer X-ray band. We also have LSST, which should come online and produce optical light curves for many millions of AGN. We have DESI and Formos, which will be getting spectra and multiple spectra of different things. So that's kind of the landscape that we'll be launching into. And I think there's some interesting synergies that can sort of happen with doing triggered follow-up of AGN that are monitored now in the optical or potentially in the X-rays to try and really get at some of the short time scale physics that might be interesting, particularly with something that is very has a lot of effective area. And Mike has turned his camera on, telling me I should shut up now. So just in terms of science objectives, we want to probe the short time scale accretion disk and corona physics. Ideally, we want to probe the short and medium time scale changes in the iron K alpha to probe potential structure changes, and then to sort of constrain the statistics at a much fainter level than eRosita will probably deliver. And in unison with surveys like LSST or ground-based spectroscopy. Okay, so I think I'll leave it there and take questions.
Okay, great. Yeah. So while people are coming up with questions, so it seems like, if we had enough AGN observed repeatedly, we could test whether, the frequency of changing log AGN changes with redshift. I mean, what constraints do we have that high redshift AGN are likely to change more or less just based on environments? Do we have anything like that? Is that something we could potentially do?
On environments, no. I mean, so the only sources, so Neil's group, did a study of sort of the frequency of changing look AGN within the deep field south, maybe within the deep field north too, with the 2 to 7 megasecond observations where you had multiple epochs. And so there were a handful that were discovered out of, let's say, 1,000 total X-ray AGN that were in that field. It was very much limited by statistics. So Axis could certainly do that in a shorter amount of time, right? And so you could have a much better monitoring campaign of those sort of 1,000 AGN. And if you had multiple deep fields, you could actually build up maybe a more reasonable sort of statistics. And you could compare that to eRosita, which should do the same for the local universe.
Okay,
Whether
great.
in terms of environment, I'm not sure. You would need to probe enough different environments to have that then be linked.
Great. So it looks like we have a hand up from Irini. Go ahead. You can ask your question.
Thank you so much. So you may have mentioned this, but how do we know where the obscuration is coming from when we're just looking at, these variability plots that you were showing earlier? How do we know we're probing torus structure versus like a cloud or clouds of star formation or things that are, within the host galaxy itself?
Yeah, so I mean, you have to calculate sort of what is the crossing time for a given, what's the typical velocity going to be of a star forming region as it crosses the corona, and it should be relatively slow. So if you see a change within days, right, that's unlikely to be a star forming region moving across your line of sight. So you'll still have that as the baseline or the floor on the obscuration. But what we're seeing is changes which are much more rapid, that are things coming in and out of the line of sight.
Okay, cool. Thank you.